Problem number 41. F of xy is equal to this vector field here. We're asked to integrate f along the boundary of this annulus right here, this kind of macaroni shaped region. We're finding the circulation of f along C. And specifically, we're told to do this using Green's theorem. So what Green's theorem will tell us is that if this is m and this is n, the circulation of f along C is equal to the double integral over r, where r is the region inside of the curve, of the partial derivative n with respect to x minus a partial derivative m with respect to y. And so as it turns out, it's going to be easier for us to compute the double integral on the interior of the macaroni shaped region than it would be for us to compute the circulation. The circulation will require us to do 1, 2, 3, 4 separate line integrals, and some of those line integrals could be nasty. This is going to be easier. Well, what is the integrand here? Let's compute that. The integrand is going to be partial derivative n with respect to x. Partial derivative of this with respect to x will be 2x plus 4 plus 0 plus 4 cosine y minus, partial derivative m with respect to y. Partial derivative of this with respect to y is 0. Partial derivative of this with respect to y is 4 cosine y minus plus 4. And at this point, we can kind of see why this problem was cooked up in the way that it was here. Why is that? Well, there's going to be lots of cancellation. So 4 cosine y, negative 4 cosine y, 4, and negative 4. And so this is just the double integral of 2x over this region. Now, how do we go about actually evaluating this integral? Well, realize that this is going to be best suited for polar coordinates. That this region right here is most easily expressed using polar coordinates. What is this region? So the inside, that inside arc there is x squared plus y squared is equal to 9. The outside arc is x squared plus y squared is equal to 36. And so what do we end up with for bounds on theta and r? Okay, so we can tell here theta is going to run from 0 to pi over 2. And then r is going to run from x squared plus y squared is equal to 9. This is r squared is equal to 9, or r is equal to 3. This is r is equal to 6. So r runs from 3 to 6. Okay, so where are we here? We have the integral theta runs from 0 to pi over 2. R runs from 3 to 6 of 2 times x. X becomes r cosine theta, and r dr d theta. And so 2r squared cosine theta dr d theta. Okay, so we just need to evaluate this. This integral should factor as theta runs from 0 to pi over 2 of let's see here, cosine theta d theta times integral r runs from 3 to 6 2r squared dr. Okay, let me go to the next slide here. What will we end up with here? This first integral will be sine theta. Evaluate that theta from 0 to pi over 2 times this integral, antiderivative that will be 2/3 r cubed. Integrate that r from 3 to 6. And so at the end of the day, this will be 1 sine of pi over 2 minus sine of 0. It'll be 1 minus 0 is 1 times 2/3 times 6 cubed minus 3 cubed. I'm sure that simplifies down, but I think that's a perfectly good final answer here. So we can see Green's theorem made our life a lot easier. That would have been an atrocious, 4 atrocious integrals to do. Look how much cancellation there was with Green's theorem.